So welcome everyone. We are back again with another session from Classiq, and today we have with us Matan Vax. Matan is a quantum software engineer at Classiq. And yeah, over to you, Matan. Would you like to give a quick introduction of yourself and then get started with the lecture?
Sure. I've been with Classiq for the last 2 years. I come from a somewhat different background of compilation and modeling languages. But at Classiq, they made me learn some quantum algorithms the hard way. So, okay, I'll get started. This is not going to be hopefully as demanding as Nadav's talk. It's pretty, it's a more elementary kind of material, more an overview of this aspect of quantum algorithms, the meaning and use of arithmetic, quantum arithmetic. And I'll be using the keyword language for it, but you can imagine, I think, all quantum languages will sooner or later have high level capture of variables, numeric variables, and expressions. So I think this is going to be the way high level quantum languages are coded. This is my outline for this talk. What is quantum arithmetic, and what's it used for, and what's unique about it? And then I'll conclude with a little more real-life example, how it's used to implement a very general building block for algorithms. Okay, so what do we mean by quantum arithmetic? We have a quantum computer. It has a certain state, and this state for us encodes numeric values. Parts of the state encodes numeric values, and then basically we evolve the state such that parts of it encode the evaluation of some arithmetic operations. So I mentioned that we encode numeric values on some parts of the state, and then we evolve the state such that it represents the evaluation of some arithmetic operations, and that's we could have said the same thing about classical computers, about arithmetic logic units, and then of course, what's special about quantum computers is the fact that quantum states can represent a superposition of numbers on these variables. And so the results that we evaluate are themselves in the corresponding superposition, so represent the space of evaluations for the expressions. And so with this superposition as part of an overall algorithm, we use all of these fun tricks to extract information and come up with the algorithm result. Let's look at a little example. I'm pretty sure that you've seen such examples from Eden or from in other contexts. But so let's go quickly over it. We have three quantum variables, numeric variables, x, y, and res here. We are putting variable x in a superposition of the values 0 and 3. You can see that I'm using just the bare prepare state function here. It's good enough for this purpose. And you can see that it's an equal probability for 0 and 3. And then I'm putting y in an equal superposition of 1 and 2 and evaluating the expression 3 times x plus y. When I synthesize this, I see a circuit that indeed corresponds to my description. So I have these two prepare states for x and y, and I'm seeing first x being multiplied by 3 and then added over to y. And executing this, I can see the basically 4 combinations of x and y, right? So x is either 3 or 0, and y is either 1 or 2. So I see the 4 combinations, and long and behold, I see also the respective evaluation of the expression in res. So it itself is in superposition and entangled with the values of x and y, with the variables x and y. So that's what I'm sampling. That's also what I'm seeing in the histogram, and you know, in the Classiq IDE, you can also see the interpretation of each state in terms of the variables, the numeric values of quantum variables. So now we have a sense of what quantum arithmetic does, essentially giving us the evaluation of an expression corresponding to the input variables, and if it's not on the same qubits, then it's in qubits entangled with them. What's quantum arithmetic used for? Well, some argue that it's completely ubiquitous in quantum algorithms, or going to be, and you can easily recognize some of the most important algorithms. So with algorithms that use oracles, you can define oracles in terms of logical or numeric expressions over some space. So that's what you can do with Grover search or quantum counting, or generally amplitude amplification algorithms. You've seen Nadav's talk using modular exponentiation, and that's used, of course, most famously in Shor's algorithm. So that's quantum arithmetic. Something somewhat different is the fact that in solving linear systems of the equation, we figure out the eigenvalues of the matrix, and then we need to invert them. So that's some kind of arithmetic. It's going to be in the amplitude, but that's a detail. We use a lot of arithmetic in all of the finance applications, so specifically to compute payoff for options. Again, all of this in coherent arithmetic. So we compute the payoff over a long period of time. There's combinatorial optimization, which is something slightly different. I won't get into that, but that's also arithmetic over quantum variables, and a whole bunch of other examples. So I think, again, as quantum algorithms become more, come to have more industrial application, the role of these kind of descriptions is going to be, really significant, major. So I just have this little example for you for an application. This is how you would code up a Grover algorithm in QMod. Simply, you already have a library of building blocks for Grover search and for phase kickback. So all you really need to do is capture your predicate and feed it into the phase oracle. And my predicate here is a 3-sat formula. So I'm searching for a bit string that would satisfy this formula, and this is generally a NP complete problem, right? So of course this is a very this is a toy example, but all I need to do is express my 3-sat formula, my logical formula directly in terms of the variables, and then feed it into the phase oracle, and then I don't need to worry about the details of how it's implemented. It's actually not easy, even for this simple case, to hand implement the unitary that computes this expression, and surely not easy to implement it efficiently, and it's going to be impossible to do it manually for larger expressions. But with these 10 lines of code, I can execute it, and in the histogram I already see that I have only 2 states being sampled, and both of which are solutions to this search problem, the bit strings that actually satisfy the expression. Okay, so that was an example of how I'm calling arithmetic also logical expressions or bitwise expressions. Consider it a general term applying to both numeric variables and Boolean variables, right? So an example of how you would use an arithmetic expression in an algorithm. What's unique about quantum arithmetic? More specifically, why is it so challenging? First of all, like everything else in quantum algorithms, it has to be unitary. It has to be reversible, and that makes it slightly different than the circuits you would do in classical computers for arithmetic. Another consideration is that you can't just drop on the floor, maybe scratchpad variables or scratchpad qubits that you use. You need to carefully disentangle them from the results, and then ideally bring them back to 0 state to be reused subsequently. That actually is related to the fact that qubits are a very limited resource, and other things are too. So overall number of gates and depth, so coherence time. These resources are very scarce, so they make the problem of implementing arithmetic, a completely different problem than in classical computing. Right, even on your mobile, there are very, very long sequences as we speak of arithmetic performed on 64-bit registers, on a whole bunch of them, and this is something that is hard to imagine even in the foreseeable future. So the scarcity of resources in quantum computers is something fundamental to the problem. We have different implementations for arithmetic operations, and I'll show you just a little example in a minute. And they reflect different trade-offs. So that relates to using your resources, your very scarce resources, wisely. And actually, these different implementations are also related to the fact that you can encode numbers or data in different ways on quantum computers. So not just digitally like we've seen in the computational basis, but also analogically in the amplitude or in the phases, and all of these are used in some of the most important quantum algorithms. So I won't go into this, but these are also for us and in QMod or in a high-level quantum language, these are also arithmetic expressions or quantum expressions generally. Let's look at the simplest possible expression, right? Res equals x plus y. If I feed it into the synthesis engine, what I'm getting is you can see the arithmetic block here with x and y coming in and the result being split across these 3 qubits. But if I expand that, I'm seeing a bunch of control nodes and Toffoli gates. But really, this implementation is not very different from how an adder is implemented classically. It's a little different actually because the addition is performed here in place. If I show you the out of place implementation, then it's really exactly a ripple carry adder that you would find in an arithmetic logic unit in your laptop. But even this is not very different. But that's what I'm getting when I'm optimizing for depth in the Classiq synthesis engine. So when I'm optimizing for width, I'm getting a different implementation, which is something you would never see in a classical computer, because the way addition is performed here is something that also Nadav mentioned. It's performed in the Fourier basis. So I'm starting off by moving into the Fourier basis of the result register, and then applying the phases, the phase rotations, so that I'm reaching the value of x plus y in the Fourier basis and coming out of it with the QFT dagger. And the reason I got this implementation is because that's optimal in terms of width. I'm not using any auxiliaries here, but it's inferior in terms of depth, because these QFT blocks are pretty deep, right? So that's an example of the alternative implementations for some of the fundamental arithmetic operations and the trade-offs that they reflect. Okay, so that just brings me to my last slide, which is just to give you a taste of a slightly more real-life application of arithmetic. So there are even a much wider range of applications for general math functions, trigonometric functions, or functions for quantum neural networks like sigmoid functions. And the problem, of course, is that we need to implement these functions coherently, so such that they actually carry over the superposition. And the beauty with basic arithmetic is that we have polynomials, and surely we have polynomials, so we can approximate pretty much any function to any degree that we want. We can develop a Taylor series, but we can do something much more efficient that's good for most purposes, which is doing piecewise polynomial approximation, even linear approximation, is good enough for many purposes, and that's what I'm implementing here. And the nice thing about it is that it's, as you can see, 5 lines of code. And the idea is that we chop up the target function in a certain domain into subdomains, and approximate each part with a linear function. And we have a Chebyshev method to come up with coefficients. And so here I just plugged in the coefficients for hyperbolic tangent, the Chebyshev coefficients for hyperbolic tangent. So I'm effectively computing here hyperbolic tangent for an arbitrary x. And I chopped it up into 4 segments. And here's the implementation. It's just figure out in which segment x falls and compute y by using the respective coefficients of the segment. So ax plus b is the linear function for a segment I, given that x falls within I, and I'm asking whether x falls within y using this label that I compute here. So I label x by which part of the domain, which segment it falls in. And of course, this is all coherent. So I can see if I feed it with a superposition of like here, if I feed my function with x in a uniform superposition of all values, I see for each of the values the respective value for this approximation of hyperbolic tangent, and that's all it took. And it's completely general. You feed in whichever coefficients for your crazy math function, and you're getting the this approximation, piecewise linear approximation for it. You can see the circuit here that we have only 4 segments here, so you can see 4 iterations of the repeat, and I expanded one of them so that you can see how, depending on the value of the label of x, I'm computing the right linear function. So that's all I have. And I can take questions, I guess, or go back to parts that weren't clear.
Great. Yeah, thanks a lot, Vardaan. Wonderful talk.